So let's say we gather all this bear data and we say, okay, the average bear weight from all of our gathered data is 99.6 kilos. So can we say potentially that if someone asked us, well, how much does a 138 centimeter long bear weigh? On average, 99.6 kilos. Well, how about if the bear is 141 centimeters? Well, the average weight is 99.6 kilos. You hear me? So you could just use the average of that collected data and just use that as an estimate for any bear in this range. You with me? But we want better, right? We want to do better. So what we did was go out and gather. We did this ourselves, right? Bears. We went out and gathered this data that includes bear length. And we want to say, okay, how much of the vertical distances, let's say we're using the mean, the average bear weight as an estimator. So that would just be this horizontal line, this horizontal kind of pinkish line you see, okay? We want to do better. So the vertical, how much of the vertical distances between each point and the line relative to the vertical distance between each point and the regression line, how much does that get reduced when we take this line and turn it into this line? We talked about residuals, right? Those are errors. Those are estimation errors. So again, the R squared tells us, percentage-wise, how much better we did from taking the average and turning it into the regression line. You with me? Does that kind of make sense? Mark's going, no. The error, the R squared value is really complicated. It's broken up into 3 pieces. It's called SST, which is the difference between each data point and the mean. It's the vertical distance between each data point and the mean. Then you've got SSR, which is the green here. It's the difference between the mean and the regression line. And then you've got what's called SSE, and that is the difference between each data point and the regression line. So it's point to mean, point to line, and mean to line. So this calculation involves all 3 of those vertical pieces, okay? And again, we agree that this is kind of a weak estimator, right? To just say every single time the weight of that bear is on average 99.6 kilos, right? No matter what its length is, we would just report 99.6 kilos. We want to do better. So we bring in bear length. And we create the regression line based on the relationship between bear weight and bear length and bear weight. Okay? So going back to, and there would be these vertical distances between every point in the data set. Okay, I just drew out a couple of them so that you could kind of get an idea what those are about. If you want to, I'll scan this and put it on my website so you can kind of refer back to it. Would that be helpful? Okay. It's a really kind of an abstract concept. It really is. It's not the easiest thing in the world, for sure. Okay, so when you get this R squared value, the 49.5, R squared is always a value between 0 and 1. It's a percentage. Okay? So what it's telling us is about 50% of those vertical distances were reduced when we took this and turned it into this. Are you with me? About 50% of those estimation errors went away when we took the mean without using bare length, and we threw in bare length, and we turned it into a regression line. Okay? So that's what R-squared does. It tells us how much better we're doing with the line than we would be doing with the average only. Okay? Shall we write that? Can I erase this? So R-squared, and remember, if you want to keep going back over this, the videos will be on my online. I'm posting the other ones as soon as I get back to my office from Tuesday's class, and the rest of them will be up within a day or so. So R-squared of 0.5, let's say 0.495, means that 49.5% of the error in estimating bare weight has been decreased or eliminated by using bare length as opposed to, and bare length, remember, is y hat, the line, as opposed to using just y bar, which is the average bare weight. Okay? You guys overwhelmed a little bit? Sorry. It's complicated, and this is why I wanted this this specific class to be videotaped, so you guys could review, and the online folks could get a sense of what this stuff's about too, because it's really hard to explain. Okay, so that pretty much takes us through the entire process. Some other cool examples of regression. I was looking around online today. There's regression was used to look at the relationship between age and blood pressure, production versus imports or production versus consumption, poverty rates versus unemployment rates, or poverty rates versus murder rates in certain communities, economic indicators versus employment indicators. So this is a gigantic topic. It's used in virtually every discipline. I've even seen where the age of a cheese could be determined by or estimated by the chemicals that the cheese is giving off. So if that can be measured, you can use that to figure out how old the cheese is. Okay, let's do this. I found some fun data. Okay, I think it's fun, all right? This data is, can you guys all see this data okay? Can you see it okay? In this data, we're going to use how many times a cricket chirps, and this is really famous data. It's very, very popular application of statistics because it's kind of fun. We're going to use how many times a cricket chirps to predict the temperature outside. Have you ever been anywhere where it's real humid and sticky in the summer? And you can hear the crickets chirp at night, and they almost, when it's really, really warm and sultry, they almost sound like it's just one continual sound because they're chirping so often. They chirp, they rub their little legs together. They have little barbs on their legs that make that chirpy sound. Remember that if you forget a data value, you have to go back and put it. This was the number. This was the number of cricket chirps that were recorded when the temperature was this. So these are ordered pairs that relate to the same instant in time, and your data values have to be corresponding across. Yeah. So the first thing we're going to want to do is graph the scatter plot. So remember that we want to know if even doing any calculations or anything is worth it. Okay, so we want to start off with a scatter plot and kind of get an indication of the potential linear relationship here. So the first thing we want to do is graph a scatter plot. Okay, so if your data is in different lists, you're going to need to go, remember, you go second y equals. You want only one plot on. You want it. You want to call up the plot that's there in your stat plot menu, and you want to put in the correct location of your x and y variables wherever they are. Doesn't matter where they are. It doesn't matter if you put L2 then L1. Doesn't matter. You just have to call them up in the correct spot. And then how do we get the thing correct on the screen? Anyone remember?
Zoom fit.
Sorry?
Zoom fit.
Zoom fit or Zoom stat. Yeah, I don't know if Zoom fit, is that working for you?
I just know it's 9.
It does? Oh, okay. The Zoom fit will work a lot when you're graphing like algebraic and pre-calc stuff. The Zoom stat, you hit Zoom and then go Zoom stat, and that'll dial in your scatter plot. Okay, so there's our scatter plot. Everyone have that? So I think Zoom stat works off of a stat plot, specifically off of a stat plot. So it looks like we've got a really good linear relationship, yeah? Looks like so x is the cricket chirps, y is temperature. So it looks like as cricket chirps more and more and more and more, what happens to temperature? It increases, right? So right now things look good. They look like they line up pretty well. Let's measure that with R. Does anybody remember how we get that? Sorry? We have to do another calculation first. How do we get the R value?
You do the y equals ax plus b.
Okay, we want linear regression,
Yeah.
right? We want linear regression, so we go stat, right, and down to number 4. And then you want to enter the location of your x variable and the location of your y variable in that order, separated by commas. Okay? X comma y. And enter.